Hi everyone, I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about solar cells. Let us see the brief outline of how we are going to discuss about this topic. First we'll see the introduction to solar cell, then we'll see the construction and then working of a solar cell. We'll discuss the VI characteristics, that is the voltage current characteristics of a solar cell. Then we'll see the applications where solar cell is being used extensively. And then we will also discuss the advantages and disadvantages of solar cell. Now coming to the definition of a solar cell. It is a cell that is also known as photovoltaic cell, and it converts light energy into electrical energy by using photovoltaic effect. So photovoltaic effect is also important. What is a solar device? It is a device that converts light energy into electrical energy by using the photovoltaic effect. Now, when we have discussed in the previous lectures regarding photodiodes are also devices that convert light energy into electrical energy. But here a solar cell makes use of the photovoltaic effect, where it will create a potential difference by using the sunlight. That is what we call as photovoltaic effect. So, photovoltaic effect can be defined as the appearance of potential difference between two layers of the semiconductor. Whenever we are taking a solar cell, it consists of two layers, P type and the N type. And whenever there is a difference in potential between the two layers, one at a higher potential and the other at a lower potential, then we say that there is potential difference between the two layers. And this effect we are calling as the photovoltaic effect. And it is basically a normal PN junction diode. We have discussed in detail about PN junction diode. So if you see its basic structure, it is a PN junction diode. Means we take a P-type material and N-type material and then combine them by different methods we have to make a PN junction. So we use one of the methods to make a PN junction diode. So it's a normal PN junction diode. Now coming to the symbol. What is the symbol we use for solar cell? So what we have here is two lines, like we see this is the positive terminal and this is the negative terminal, and they are enclosed in a circle, and we have two arrows that denotes that light is falling on the cell, solar cell. So here we say it is sunlight because we are saying solar cell. So sunlight, when it falls on the cell, that gets converted into electrical energy. So whenever we talk about symbols for a basic PN junction diode, we have seen the triangles. This is positive and negative. This is for a PN junction diode. And then when we use this as an LED, when the PN junction device is an LED, light is emitted. So we have two arrows that are pointed outwards. This is an LED. Now when it comes to a photodiode, again we have a triangle with a line, positive, negative, and here we have two arrows pointed towards the junction. That shows it is a photodiode. All these symbols should be very clear, because whenever we are using a solar cell or a LED or a photodiode in a circuit, we will have to use the symbols. So these are the symbols for different devices. Now coming to the solar cell, it consists of a glass or plastic cover. So we will see step by step. You can see the diagram here. So the first one we are calling as what is shown here, this part. Now, this is the cover for the solar cell. And then we have an anti-reflective coating. So there is an anti-reflective coating. This is the anti-reflective coating. You can see here anti-reflection coating. And between the two, we have a transparent adhesive. Adhesive is to hold them together. So this is a transparent adhesive. So the first one is the cover glass and the second one is the anti-reflection coating. Then we have the front contact. Front contact is to allow the electrons to enter the circuit. So this is the front contact. This part which we see here, this is the front contact. This will help the electrons to enter into the circuit. And then we also have a back contact. So back contact is used to complete the circuit. So this is the back contact. The back contact is this, which is used to complete the circuit. So if you see here, the circuit is connected like this. Whenever we have to capture the current, we need to complete the circuit. So we are connecting it from the front contact and to the back contact. And you connect a load here or a lamp here, you can see the current. And then the semiconductor layers. We have different semiconductor layers. So what are the semiconductor layers we are seeing here is the N-type semiconductor and the P-type semiconductor. So here, this is the N-type semiconductor and this is the P-type semiconductor. One is this and the other is this. Two layers we have, N-type and P-type, where the electrons begin and complete the journey. So this is the structure, the entire structure of the solar cell. Different parts are very clear in the diagram. Now let us see how they are made. It consists of N-type and P-type material, and N-type is highly doped and P-type is lightly doped. So when we say N-type is highly doped, what is the meaning here? Whenever we are talking about N-type material or N-type semiconductor, we are adding a pentavalent impurity. Pentavalent impurity means an impurity which has 5 valence electrons. This is the impurity we are adding. And doping means it is the process of adding an impurity to a semiconductor. So we have taken a pure semiconductor and we are adding the pentavalent impurity to that semiconductor. That process we are calling as doping. And when it is highly doped, what is the meaning of highly doped means? The concentration of the impurity atoms that are added are more. Then you say it is highly doped. And then we are taking P-type material. When I say P-type here means we are adding a trivalent impurity. Trivalent impurity will have 3 valence electrons. There are 3 valence electrons. But the number of atoms of the P-type that are added are less. So we say it is lightly doped. So we are taking N-type material which is heavily doped and the P-type which is lightly doped. The concentration of the atoms is less. Now the top and the bottom layers is of conducting electrode. So the top layer and the bottom layer, we have already seen them in the previous figure as front contact and back contact. So they are of conducting electrode to collect the current. So whenever we are having, this is the front contact and this is the back contact, they are connected with conducting electrodes. Now, the bottom is fully covered with conductive layer and the top layer is not fully covered. When we are taking the front layer and the bottom layer, this bottom layer, this is the bottom layer where we are having the contact, back contact. This is fully covered with the conductive layer. But the top layer, this is the top layer. This top layer, if you see, this top layer is not fully covered. Why we are not fully covering it is because the sun's rays has to enter into the cell or into the layers through this end, and these rays should not be blocked. So we are not covering it. We are keeping some openings so that the sun rays can penetrate inside. Then, since semiconductors are reflective in nature, so whatever falls on it, these semiconducting materials may reflect. So now this part is also coated with anti-reflecting material. Why anti-reflecting? Whatever the sunlight that falls on the surface should not get reflected back. So it should be penetrating into the junction. That is why we use anti-reflective coating. So if you see here, this is the N-type silicon we have. This part, the top part is the N-type and this bottom part is the P-type. If you see the cross section here, this is P-type. And the front side and the back contact are connected to a load or a voltmeter to observe the potential difference. And this top part is not fully covered with conductive material. So we are keeping some openings so that the light, the sunlight will fall onto this and then goes inside the material. And the working of a solar cell is based on photovoltaic effect. So now we are going to discuss about the working. So the working depends on what? Photovoltaic effect. What is photovoltaic effect? It is nothing but the generation of potential difference at the junction of two different materials in response to the visible radiation or any other radiation. So here we are talking about the solar radiation. So whenever the radiation falls onto the junction of two different materials, there will be a generation of potential difference. So that we are calling it as photovoltaic effect. And through this effect, the solar cells convert sunlight into electrical energy. Whatever light we are getting is from the sunlight. So the solar, the name solar comes from the solar light or the sunlight. So these are cells which are converting the sunlight into electrical energy. Now, how this solar cell works? A depletion layer is formed at the junction of P-type and N-type. So if you see in the figure here, this part is the N-type. This is the N-type semiconductor. We are taking two different layers, N-type and P-type. So we have the N-type layer and then this green part is the P-type. So this is the P-type semiconductor. Now when we are bringing this P-type and N-type together, in a normal p-n junction, what happens? There will be movement of electrons from the N side onto the P side and movement of holes from the P side to the N side. This we call it as diffusion. Diffusion because it is always the movement of charge carriers from higher concentration to lower concentration. On the N side, we have electrons as the majority carriers. So electrons move from N to the P. And on the P side, we have holes as the majority carriers. So holes move from the P side to the N side. So when this diffusion process happens, there will be immobile charge carriers that are left on either side of the junction. So on the N side, we have positive immobile ions, and on the N side, on the P side, you have the negative immobile ions which are stuck to the crystal lattice. Because of that, there is a depletion layer that is formed. So this is the depletion layer. This part, this region, we call it as the depletion region. This region is depleted of the charges. So we call it as depletion region. So light energy of the sun's rays fall on the solar panel as photons. So whenever we are talking about radiation, we have already studied about the Planck's theory. Planck gave us a beautiful theory which says that whenever light is emitted or absorbed, it is always emitted in the form of photons. Photon is nothing but a packet of energy whose energy is given by E is equal to h nu. So E is equal to h nu. This is the energy of photon. So when energy is incident on the surface, it is incident in the form of photons, and that can be calculated using the formula E is equal to h nu, where nu is the frequency of the light, and h is the Planck's constant. H is the constant which was given by Planck, so we call it as Planck constant. And the energy of these photons is higher than the energy gap, and they give energy to the electrons and holes in the depletion region. So whenever we see the energy band diagram, so if I draw the energy band diagram here, this is the valence band and this is the conduction band. We say this is the lowest level in the conduction band and this is the topmost level in the valence band. And this region, we call it as energy gap. So valence band here always denotes the energy levels of all the valence electrons put together, and conduction band denotes the energy levels of all the conduction electrons, which are free electrons. Now, whenever we have to make an electron free from the valence band, we have to supply an energy equal to or greater than the energy gap. Only then the electron can move from the valence band to the conduction band. So whatever the energy of the photons that is incident is higher than the energy gap, so that they give energy to these valence electrons to go into the conduction band. So when an electron moves from the valence band to the conduction band, there will be a hole that is generated here. Okay, so this is the process that happens. Now the electrons move towards the N type and the holes move towards the P type, and they act as battery. Now what we are seeing here is when the energy is given to the holes and electrons here, all the electrons that are there here, they move towards the N side. These electrons, they are moving towards the N side. Electrons move towards the N side and the holes will move towards the P side. These holes, they are positive. They are moving towards the P side and they will act as a battery. Whenever there is separation of charges, on one side you have the positive holes. Holes are nothing but deficiency of electrons. We consider them to be positive. And electrons are negative. So whenever there is separation of charges, then it acts as a battery. And the movement of electrons always gives rise to electric current. So the current here that we are getting is due to the movement of these electrons. Now we will understand the basic processes behind the photovoltaic effect. We will understand what are the different processes that are happening in this photovoltaic effect. They are very simple but yet very important to understand very clearly. So the first step here is the generation of the charge carriers. So how these charge carriers are generated? It is due to the absorption of photons in the material. So when sunlight falls onto the surface, that is absorbed in the form of photons by the material. And the second step, we have the separation of photo-generated charge carriers. Photo-generated means here they absorb the light and then they get separated as electrons and holes. So this separation happens. Then after that, the collection of photo-generated charge carriers at the terminals of the junction, which gives rise to current. So these are the processes. Let us understand them step by step. Now in the first step, what we are seeing, photons in the sunlight hit the solar panel. What is a solar panel? The topmost surface, we are not covering with a fully conductive layer, but we are putting the panels which will absorb these photons. So when photons in the sunlight hit the solar panel, they are absorbed by the semiconducting materials such as silicon. We are using these p-type and n-type semiconducting materials. So they are absorbed by the semiconducting materials. And then in the second step, what we are seeing, the electrons that are negatively charged are knocked loose of their atoms, causing an electric potential difference. So when the electrons become free, they are separated. So in the second step, basically we are seeing the separation of charge carriers. So when the electrons become free from their atoms, they start moving. No, and that creates a potential difference and current starts flowing through the material. And due to the special composition of solar cells, these electrons are allowed to move only in one direction. Okay, so they will be moving only in one direction because the direction of the flow of electrons decides the current. Then in step 3, what we are seeing here is an array of solar cells. We will never use one single cell. We will be using many cells. Like when we talk about a battery is nothing but a number of cells which are placed together. Okay. The same way here, we are using an array of cells which convert the solar energy into direct current, which is in the usable form. We call it as DC electricity. So the array of cells convert the solar energy into direct current, which we call it as DC current. Now let us see the explanation with the help of this diagram. So first what we have seen, the PN junction is exposed to light and the photons are absorbed and electron pairs are generated. These are the 3 processes we have seen. So now you see here, we have taken this layer. So this is the N layer. 2 types of layers we have to take, N layer and this is the P layer. So 2 layers. So a junction is formed. This is the junction and this is the depletion region. So now this junction is exposed to light. So light is allowed to fall. It will penetrate and reaching the junction. Now light is incident in the form of photons. And these photons are absorbed by the charge carriers in the depletion region and electron-hole pairs are generated. You can see the hole and electron pairs that are generated. So these electrons and holes that are produced over a small distance from the junction, they reach the space charge region X by diffusion. So they start diffusing. So how the electrons will move on to the N side? You see these electrons, they are moving on to the N side. Diffusing we call. And then these holes, they are moving on to the P side. So the electron hole pairs are separated by the strong barrier field across the space charge region. And the electrons in the P side slide down the barrier potential. Now here we will try to see the energy band diagram. Whenever we have seen an energy band diagram, on the P side, it is always at a higher energy level than the N side. So this is the N side and this is the P side. So we are seeing the energy band diagram for a PN junction which acts as a solar cell. Now, here this is the barrier. This is the barrier layer, or we call it as the potential barrier. So, P type, N type, and then there is a barrier here. Now, when the photons are incident here and there is separation of the electrons and holes and they diffuse onto either side, what we are seeing here is the holes that are here will slowly slide down the potential barrier. Now, holes from the P type, they are moving on to the N side. And here in the N side, whatever we have electrons, they are moving on to the P side. So there will be movement of charge carriers. And when the PN junction is open circuited, so accumulation of electrons and holes on the two sides of the junction gives rise to an open circuited voltage. So when it is open circuit means we have the generation of charge carriers. Now this is the N-type layer, I can say, and this is the P-type layer, bottom, and there is separation of the charge carriers, and this is open. So there will be accumulation of charge carriers like this. And whenever a load resistance is connected across the circuit, then there will be a current flow in the circuit. You connect a lamp or something here, then there will be current flowing and you can see the lamp glowing. Now the maximum current is called the short circuit current. So when do we get a maximum current? Is when the electric short is connected across the diode terminals. And current flows along the diode as long as it is exposed to the sunlight. So as long as the diode or the solar cell is exposed to sunlight, there will be current, and the magnitude of current is always proportional to the light, intensity of light. So more the intensity of light, more the amount of light that is incident per unit area, more will be the current. So current is proportional to the light intensity. So let us understand with the help of this diagram the entire functioning of the solar cell. In the first diagram, we are seeing a PN junction solar cell with load resistance. No, we have seen if there is no load resistance, we will not see the current. So we have the P layer, we have the N layer, and these are the contacts, front contact, and this is the back contact. We are connecting it to a load resistance. So when sunlight falls on the junction, then what happens here is separation of charge carriers, movement of charge carriers, and generation of current. So in the second, what we are seeing here is the diffusion of electrons and holes. So the electrons are diffusing into the N region and the holes are diffusing into the P region. So in the second step, what we are seeing is the diffusion. This is the space charge region X we call. And then we are seeing the energy band diagram. In the energy band diagram, what we have seen, this is the P side. Of course, there we have seen on the reverse side. But here, this is the P side and this is the N side. So now you have the movement of holes from P to the N and from here, electrons from N to the P. So this is how the movement occurs. And whenever there is movement, there may be emission of light. Okay, so for formation of the open circuit voltage, so whenever it is open circuit, these charge carriers are separated, because of which there is a potential difference. We have seen what a photovoltaic effect is. In a photovoltaic effect, we are seeing there exists a potential difference. This is the potential difference we are observing at the junction because of the light. So here also we are seeing, due to the light that is incident, we are observing the difference in potential. Now coming to the VI characteristics. What are VI characteristics? Voltage versus current. Voltage versus current. We are going to plot a graph for voltage versus current. we are taking the voltage along the x-axis. This is the x-axis. We have taken the voltage. And this is the y-axis. We have taken the current. Along the y-axis, we have taken the current. So what we are going to observe here is, as the voltage increases, how the current varies. So VOC is the open circuit voltage, and it is measured when no load is connected. So what is open circuit? The name itself says that it is open, means there is no load that is connected. So here in the diagram, if you see, VOC is the open circuit voltage. So at this particular voltage, the current is 0, means there is no current. So when there is no load connected, there is no current. Then PM is the maximum power. IM is the maximum current and VM is the maximum voltage. So this point, this voltage is VM, which is the maximum voltage, and this point, this is the IM, which is the maximum current. So we know that power P is given by voltage multiplied by current. So this is observed at the bend of the curve. Whatever curve we are getting by plotting the voltage versus current characteristics, at this point we have the maximum power, and this maximum power is given by Vm into Im. So when the solar cell is open circuited means it is not connected to any load, the current is minimum and it is 0. The first point we need to understand. When it is open circuited, VOC, open circuit voltage, the current will be 0. And the voltage across the cell is maximum. When is the voltage across the cell maximum? It is known as the open circuit voltage, VOC. So this is the maximum voltage we have, and we call it as the open circuit voltage. Now at the other extreme, when the solar cell is short circuited, means when we are connecting it to the positive and the negative leads together, we say it is short circuited. The voltage across the cell will be minimum, but the current flowing out of the cell is maximum, and we call it as short circuit current. So where is the short circuit current? This is the short circuit current. So I'll say this is maximum, I max. What I max denote is the maximum current, which we call it as short circuit current. And this short circuit current occurs at minimum voltage 0. So this is the maximum voltage, which we call as open circuit voltage. This is the open circuit voltage. And this is the maximum current, we see, that is the short circuit current. Now these IV characteristic curve ranges from short circuit current, that is ISC at 0 output voltage, to 0 current at full open circuit voltage. So this is the open circuit voltage maximum, and this is the short circuit current. So it is ranging from here to here. So the maximum voltage is available in the open circuit, is at the open circuit, and the maximum current is at the closed circuit. This is a very important point to remember for a solar cell. So now if we have to calculate the electric power, there is some point where we get the maximum power. We have already seen this. So this is the point where we are getting the maximum power. This corresponds to maximum voltage and this corresponds to maximum current, and the power is obtained by the PV curve, we say. So the area under the curve gives us the power, V MP multiplied by IMP. That is the maximum current and the maximum voltage gives us the maximum power. So this we are calling it as the maximum power or MPP. Now when we are talking about this diagram, this shows for a typical solar cell, that is a silicon photovoltaic cell which operates under normal conditions, and the power delivered is always given by I into V or V into I. Now the maximum power of the solar cell is positioned near the bend. What are the values that we are going to see? So the corresponding values VMP. VMP represents the voltage maximum for the maximum power, and IMP denotes the current for the maximum power. So VMP is approximately equal to 0.8 to 0.9 VOC. That is the open circuit voltage. And IMP is approximately 0.85 to 0.95 ISC. That is the short circuit current. And this voltage, the output voltage and current, both depend on the temperature. So when the temperature varies, so the output voltage also varies. That means the power will also vary with the temperature. So when the voltage and current varies with temperature, that means power also varies with temperature. Now coming to the applications, where all we are going to use the solar cells. They are extensively used in satellites and space vehicles. So in satellites and space vehicles, we use solar cells because they need long duration power supply. So continuous power supply and long duration. That is why we use them in satellites and space vehicles. Also for domestic purposes, we use solar cells. Then the common materials that we are using are silicon, gallium arsenide, cadmium tellurium, and copper indium selenide. These are compounds of the materials we are using, and this is pure silicon. And what is the criteria that we'll have to consider for selecting the material that we are using in the solar cell? What should be the criteria of the materials that we are using for solar cells? The first one is the band gap should be from 1 electron volt to 1.8 electron volt. So it's a moderate. The band gap is 1 electron volt to 1.8 electron volt. And it should also have high optical absorption. Means the absorbing capacity should be high. When light falls onto the surface of the solar cell, it should have the capacity to absorb. So the material should be like that. It has to have a high optical absorption. And also it should have high electrical conductivity. Why electrical conductivity? If the conductivity is high, it will allow the electrons to flow freely, and then we have the current. So these materials should have high electrical conductivity. And then coming to the availability, it should be available in abundance. They should not be rare materials. No, they should be available in abundance. And the cost, finally, when it comes to the manufacturing, the cost effectiveness has to be there. So the cost of the material also has to be low. Then the advantages of a solar cell. What are the advantages of solar cell? No pollution. No, that is why we also call it as green energy. And it should last for a long time. No, there should be continuous supply. So it should last for long time. And there is no maintenance cost or minimum maintenance cost, we can say. And what are the disadvantages? Disadvantages of the solar cell. It has high cost of installation. So whenever you will have to make a solar plant, the installation cost is high. That is one disadvantage. And it has low efficiency. The efficiency is low because there may be losses. No? So during a cloudy day or during the night, the sunlight is not there. So we will not get the solar energy. On a cloudy day or during the night times, when solar energy is not available, then we will not get the energy. So this is one disadvantage of solar cell. So for more information regarding this topic, you can refer to Principles of Solar Cells, LEDs and Diodes by Adrian Kittai, by Ville Publications. This book gives a lot of information regarding this topic. For any clarification or information, you can refer to this book. Thank you and see you again.
Like, share, and subscribe. Hit the bell icon for more updates.